technical difficulty. But it's a pleasure to be here this morning, and I want to start by thanking the organizers as well very much for the invitation to tell you a little bit about the work that we've done in terms of the laboratory and astronomical spectroscopy of molecular ions. And the work in the laboratory is mostly done here at the Center for Astrophysics, and as you'll see, most of the astronomical work has been done in collaboration with astronomers here and abroad. And it's important to emphasize this is actually a fairly new field that's only about 5 years old in terms of detections of negatively charged molecules in the interstellar medium. So I'd like to kind of go through, at least briefly, and give you a kind of historical perspective of how we got to the point that we are in terms of laboratory spectroscopy and ultimately the astronomical spectroscopy, which has advanced quite quickly in the past few years. So as Eric already alluded to, in fact, in 1939, before we knew anything about molecular astrophysics, before molecules, even diatomic molecules, were detected in space, it was shown by Rupert Wilt in 1939 that H- is the source of optical opacity in our sun and similar stars. So that is, if you look at the sun, and I do not recommend you do that regularly, that is in fact the species which gives rise to the opacity. Shortly after that realization, in the early 1940s, CH, and CN were detected optically, and then there was a long hiatus, and then molecules were detected in the late 1970s, or late 1960s and early 1970s, and we have this tremendous amount of activity of quite extensive laboratory spectroscopy and astronomical spectroscopy with detections of about 150 molecules as of about 2006, and most of those are neutral molecules. We've already heard many of them are exotic and unusual by terrestrial standards. About 10% of them are protonated or positively charged. But no negative molecular ions were detected in space during that long period of time. It's important also to point out that, in fact, negative molecular ions were predicted theoretically by a number of groups, by, in fact, a number of people, several people who are here, in fact, to be constituents of the interstellar gas. And under the right conditions, they could be made in a wide variety of astronomical sources, and they, in fact, could be quite abundant. People like Eric and Alex, in fact, predicted this many years ago. In terms of the laboratory spectroscopy, in fact, there is a tremendous amount of work done on negatively charged species, right? I mean, this is a very important thermodynamic quantity for physical organic chemists to determine the electron affinity of molecules, and there's been recent tabulations, and there's well over 1,000 of these that have now been determined. The electron affinity has been determined, but that's at very low spectral resolution. So what we want to do, obviously, is to, from the astronomical perspective, have very precise laboratory rest frequencies, often in the radio band, because this is the transitions which are most intense in space, and so that astronomical searches can be done very efficiently. So if you look, in fact, of these 1,000 or plus molecules that have been detected in the laboratory, what fraction of them are known at a very high spectral resolution? In fact, only 2 have, up till 2007, had been detected in the radio band, and their rotational spectrum very precisely determined, and that is OH- and SH-. There were a few more which were detected in the infrared, and the rotational structure was resolved, and therefore the rotational constant was derived fairly accurately, not quite to the accuracy which we'd like, that is to a fraction of a kilometer per second in terms of equivalent radial velocity. That is, we want to know the line frequency to a fraction of a line width. And this was mostly work by the Sakeley group, things like NCO-, NCS-, and a few others. In addition, there was rotationally resolved electronic spectroscopy done by the Boulder group and by John Meyer as well on a few simple species as well, which had some rotational resolution and therefore derived, again, an estimate of the rotational constant. In terms of publishing, or at least searches in space, there probably are many more, but the only one that we're aware of that was published was an unsuccessful search for small negative molecular ions, based, again, on either calculations or on infrared data. And that was done in 1995. And the idea there was, again, to follow the history of detections of molecules in space, small molecules that are typically detected, and then ultimately larger ones as well. So you built up from small chains to larger chains. Which brings us to, in fact, a very nice paper, again, more than 15 years old now, by Ken Kawaguchi and his coworkers, in which they looked at this very rich source IRC plus N216, which you've already heard a little bit about, which is a central star CW Leo. You can see it kind of right here. It's one of its last stages of the cellular evolution, what they call the AGB, or high mass loss phase. So it's surrounded by a thick circumstellar shell of gas and dust, and it's sufficiently close to us, in fact, with powerful interferometers, which I'll show you a little bit more about in the talk. You can, in fact, spatially resolve and do time-dependent chemistry and look at the distribution of molecules as a function of time from the central star. And you see this, a variety of maps have been made for these fairly exotic species like magnesium NC, CCS, and some of these carbon chain molecules as well. Most of them are in this outer circumstellar shell of this evolved carbon star. What they did is a spectral line search. They simply looked at over a range of frequencies, detected a number of lines, and tried to assign as many of them as they could to known species, whether they be in the ground state, the isotopic species, or vibrationally excited state. And in fact, we know this is an extremely rich source, about 50 or so molecules. About a third of all molecules have been found in this source. And they were very successful in detecting many, many molecules. However, there was one, actually two, but one more interesting series was found for which they could not assign to any known species, any isotopic species or vibrationally excited state. And that two of the lines in the survey are shown here. And it's important to emphasize that the structure of these lines is not due to the underlying electronic structure of the molecule, but rather the fact that this is a circumstellar shell and there's gas coming towards you and away from you. And that's what this double peak line shape indicates, that the molecule is formed in this circumstellar shell. And there are, in fact, a very simple relation between the frequencies of these lines. They're ratios of integers. So, this is kind of freshman quantum mechanics here. From this simple relation, you would conclude that the ground state is a closed shell singlet sigma molecule. And from the rotational constant you derive, you get a B value of 1,377 megacycles, which is within 1% of this very well-known radical in the source, C6H. So an obvious candidate, based on those two facts alone, is C6H minus. Right? So you have an open shell radical, you add an electron, and you form the closed shell ground state. And it seemed, however, that this explanation was dubious in the extreme, in the sense that history really does repeat itself. It's remarkable how often that happens. And it parallels really the early history of interstellar molecules and the objections as to why molecules themselves could exist. Right? First of all, the absence of evidence becomes potentially the evidence for absence. No molecular ions have been detected over a period of 30 or 40 years. Therefore, and there have been searches for these small ones, so why in the world would you have a negative molecular ion? Second, it seemed very unlikely that the first negative molecular ion that would be found would be such a big molecule, at least by interstellar molecule standards. It was larger than most of the neutral molecules and all the cations. Another parenthetical point is that people had often thought that the fractional ionization in the source was very low, because HCO+, which uses a measure of the fractional ionization, is in fact very, very weak. So people said it's not even a very weakly ionized source. And third, of course, is this well-known explanation for all phenomena, right? We don't know how molecules are made, but we know how they're destroyed. We simply expose them to starlight, they fall apart. So if you're not careful, that's a rate equation, right? I know how they're formed, I don't know how they're formed, but I know how they're destroyed, therefore the steady state population is 0. Right? And that's exactly what was used in the early days as to why molecules themselves couldn't exist. And then finally, since this is a fairly exotic explanation, at least on the surface, you really need laboratory data to be absolutely certain for this identification. So we had really struggled with this series and tried to explain it by different means and more exotic explanations. And the real advance was not any laboratory work, but actually detection of this series in a second astronomical source, the source TMC1. Again, a very rich source for molecules, but a much different source, a cold molecular cloud, not a circumstellar shell. And we were actually looking for something else, but we knew, in fact, that the lines, if they occurred, would be within the band of the search. And there are two fairly weak lines that we found with a modest amount of integration time. And these are exactly the frequency you expect from the higher frequency IRC plus N216 data. What's important is that it really rules out a metal-bearing molecule. As I've already indicated, there's things like magnesium and calcium. Silicon molecules are found in IRC. Very few, if any of those, are known in this source. Secondly, this is a cold molecular cloud with a very low rotational temperature. So you now know you're looking at low J transitions, and these are razor-sharp lines, and there's no structure to these. So you can rule out that there's some accidental collapse of structure of some kind. And you can be certain it's really a closed shell sigma ground state. And in some general sense, it tells you now we found this two series of lines, the same carrier in two different sources. So it's arguably a more fundamental molecule. So on the basis of this second astronomical detection, we were confident, I should say, that the carrier had to be C6H minus. Not because we ever embraced C6H minus, simply because there were no other candidates left. All right, so I won't go into detail here, but we use a technique, several techniques in our laboratory. The most powerful, one of the most powerful methods we and other people use is Fourier transform microwave spectroscopy. And the idea is you simply couple a supersonic molecular beam to a discharge source. And this is a very efficient way to make larger molecules, radicals, carbines, highly energetic isomers, protodata molecules, and ultimately negative molecular ions as well. So they break apart, reform, and a variety of species are produced in this cold adiabatic expansion. The temperature is a few degrees Kelvin, and that's well coupled to the frequency range of this device, which is in the centimeter band, typically 10 or 20 gigahertz. And then we apply a pulse of radiation and listen for this echo. And just like in the IRC case, our laboratory lines are doubled because of a Doppler effect. We have an axis of expansion along the cavity axis. So it's a very high sensitivity, high resolution way to detect the rotational spectra of unstable molecules. And what we're able to do is to detect with this device, as well as a long path DC glow spectrometer, in fact, lines in the laboratory with both of those spectrometers with two different hydrocarbon gases that are exact frequency agreement with the astronomical lines. All right, now the beauty of this, again, freshman chemistry, there's two parameters to describe the spectrum of this molecule. It's a classic rigid rotor. You have a rotational constant and the very small correction for the fact that it's not infinitely rigid. Right, and you can see from here the laboratory spectra, obviously these are very sharp lines, so there is perfect agreement between the laboratory and astronomical. The astronomical is somewhat more uncertain because the lines in IRC are somewhat broader. And this is an indication that between the laboratory and astronomical, and the lines that we derive are with half a channel width in this source, TMC1. So there's no doubt we've detected in the laboratory the carrier that's giving rise to the lines in TMC1 and IRC plus inter-16. The only question becomes, what is the carrier? Right? And it's fairly obvious what the carrier is. We use hydrocarbons, so it contains carbon and hydrogen. We know that the lines are linearly related, therefore they have to be, all the heavy atom weight has to be along the same axis, the A rotational axis. We know it has to have 6 and only 6 carbon atoms because more or less the rotational constant is off by tens of percent. And we know it contains hydrogen specifically because we can replace hydrogen with deuterium, and the line disappears and another line appears, and that shift is characteristic of hydrogen at the end of the chain. So then we're left simply with the neutral and the both positive or negatively charged variant. Obviously the radical is well known, and C6H plus has a triplet sigma ground state, not in agreement with what we observe. So by default, it has to be C6H minus. So arguably, we go from not knowing what the carrier is in a matter of a few weeks to the fact that now you can argue that C6H is arguably one of the most securely identified, best identified or securely identified astronomical molecules. We have very good laboratory spectroscopy to support the astronomical work. Okay, so an obvious question then to ask is, well, why C6H minus? What properties does it have that make it, in this case, detected in these two sources? And there are basically 4 factors. Number one is, it's been argued that you might expect a larger molecule like this to be formed by radiative attachment. Therefore, if true, then you need the radical to be present. In both sources, C6H radicals is abundant. Second is a point which is a departure from kind of traditional neutral and cation chemistry where we build up from small molecules to large molecules, and that is size confers stability. Apparently, C6H minus is large enough whereby this attachment of electron does not destroy the molecule. And that process becomes at least somewhat efficient. Third is, in some sense, C6H minus is not very, well, it's a highly stable anion. It's got a binding energy that's been measured, and it's nearly 4 electron volts. Right? That is a very large number. And fourth is, I'll show you in a moment, is this idea of spectral simplification that we get upon electron attachment, whereby the lines of the anion are 10 times more conspicuous if both the neutral and the anion are present at the same level of abundance. So this is just a simple cartoon here showing you, of course, the basic idea that if it's electron attachment, you add this electron, you get this acetylenic-like structure. It's basically triacetylene, where you're moving this proton out to infinity, and this electron pair occupies this very tightly bound sigma-type orbital on the carbon with s character. And again, the electron affinity is extremely high compared to most molecules which have been measured. Second is this idea of spectral compression. So this is actually a spectrum in IRC plus 10216 for C6H for a single rotational transition. And it has, again, this total of 8 lines, counting the Doppler from the source, 4 of which arise from the fact that it's a doublet sigma inverted ground state with a doublet pi 3 halves, lower energy, and it's warm enough, in fact, that you also see transitions from the doublet pi 1 half, and you have hyperfine structure from the hydrogen. So you have 8 features. However, when you add this electron, what happens is all this structure, nearly blinded myself here, all this structure collapses into a single feature here, right? So this is the same line of C6H minus. And again, you have this very simple structure here. So all the structure collapses down here. In addition, you take a polar molecule and you make it even more polar upon electron attachment. So the calculated dipole moment is about 5.6 for the radical, and it's about 8 dBi for the anion. Detection sensitivity in space goes as a square of the dipole moment, so that's another factor of 2, meaning roughly about a factor of 10 enhancement upon electron attachment, which is obviously helps very much detection in space and in the laboratory as well. Eric kind of touched upon this topic, but electron radiative attachment calculations have been done, assuming kind of a 2-step process where we add in his calculation, where we form the temporary negative ion, and then we ask the question, what is the probability that it will form the anion at ground state, or will it simply auto-detach the electron? And what he finds is, in fact, as you increase the chain length, owing arguably to some kind of generalized density of states argument, the probability that it will detach the electron goes down precipitously, and the overall rate of electron attachment rises to a fairly constant level after of order of 5 or 6 or so, or 4 carbon atoms. So this process of electron attachment in his calculations seems to be relatively high once you reach some modest size chain length. So what are the implications from this discovery? What should we do in the laboratory? And for that matter, what should we do in space? Well, what we should do is we should obviously try to detect other molecules or other ions that have these same basic properties, right? We should, in fact, try to observe anions for which the radical is well known in sources. We should, hopefully, when we add the electron, we'll get a closed shell sigma ground state. We'd like the dipole moment not ideally to go up a lot, if not go down not too much, and we want to focus on those with high electron affinities. All right, and so in fact, these are the properties of these shorter and longer members in the series, as well as CN and C3N. And you see electron affinities are all quite high. The dipole moments of the anions are extremely large. Notice C8H minus is about calculated to be 12 dBi, and they're all closed shell sigma ground states. I should point out C6H minus among these series is actually the least favorable case with respect to this spectral compression. If you take C4H, for example, it's a doublet sigma ground state, and it's a doublet singlet sigma upon electron attachment. So the ratio now, you go from 0.9 to 6 dBi squared, is a huge enhancement. So C6H is actually the least favorable case where you only get a factor of 10. And so what we've done now in the laboratory is, in fact, measure at high spectral resolution the rotational spectrum of all of these carbon chain anions, from C2H to C8H, as well as CN minus and C3N minus. And not a carbon chain, but a related species, we found now the rotational spectrum of NCO minus as well. And I won't go into detail here, but we do the same kind of tests in terms of harmonicity, elemental composition, isotopic shift. In many cases, we can directly determine the ionization state by looking at the ion drift of these species. So these are all secure and now have all the data we need to start looking for them in astronomical sources. And although it was, as often the case, because astronomical time is competitively granted, the laboratory spectroscopy proceeded more quickly, and now the astronomical spectroscopy has really caught on. So what I'm happy to report is the only one that's not been detected in space of the carbon chain anions is C2H minus, and we believe that, in fact, C5N minus has now been probably found in IRC plus 10216, though we don't have laboratory data to absolutely confirm that. as I'll show you, and as Eric has alluded to, in fact, the abundances are fairly constant and in some cases very high, specifically for C8H-, where about 35, of order a third of the molecules are negatively charged in this, for C8H. And the recent detection of Cn- in IRC in fact suggests it's present about 0.2% relative to the radical. That is not consistent with radiative attachment and suggests a formation route involving carbon chain anions and the reactions with nitrogen, which has been studied by the Beerbaum group. So again, this is a summary that Eric showed, in which we've now plotted the ratios of the anion to neutral in both TMC1 and IRC plus into 16. And you see for the longer chain molecules, the agreement between the calculations and observations is fairly good, within a factor of a few in most cases. But when we go to the shorter chains, C4H- in particular, the ratio is far from that calculated. The observation is far from that calculated. And that not shown here is, of course, the case of Cn- as well. And so that's telling us, obviously, there are formation and destruction mechanisms that we certainly do not fully understand, and reaction rates that we perhaps need to measure. So what we've been able to do, and with others, is now, in fact, ask the question, are these two sources special? Or can we detect negatively charged carbon chain species in other sources? And the answer is, in fact, they have been found in other sources. We found them in at least 8 sources already, where other people have, mostly in dark molecular clouds. And the ratio is typically kind of 1 to 5%. And so with better sensitivity, we think, in fact, C6H- as a surrogate for negatively charged species, we can find them in many sources. Okay, that they're probably widely distributed at this level or comparable levels. And what we did a wider search looking at a number of sources, and we found an empirical correlation between the negative ion, the radical, the associated radical, and the shorter members, suggesting there's probably this sequential formation route, production of C4H to C6H, and then perhaps electron attachment to form the negative ion. And this is just one example in the source Lupus 1a, where you see again by Sakai and others detection of C6H-. And we can also, of course, learn about the fractionalization in an analogous way to what is used for positively charged species to derive the fractionalization arguably more directly, because we're looking at the negative charge. And the value that we derive in these sources is actually fairly similar to that derived from HCO+. All right, so we can also then, ions are now being incorporated into models. Eric has done this, in fact, and this is simple schematic is shown here, but the point is that negatively charged molecules, carbon chains, provide us with new formation but also destruction routes. And this is just one example where they calculate the production of various acetylenic-like chains with and without anions, and it appears as if at least negatively charged molecules are a way in which we can form with greater abundance still larger molecules, arguably because the negatively charged species is a more gentle collision partner than our electrons. All right, so I think that work is continuing and moving forward in terms of the role that anions now play in this more complex chemistry. As we alluded to, we can determine things like the rate of radiative attachment, and we can infer the ratio or the fractionalization, because the ratio of the anion to neutral has been shown by several people is a very simple relationship related to the rates of destruction, in this case with atomic hydrogen predominantly, and radiative attachment. And so if you can get estimates of 3 of the 4 factors, you can infer the rate of radiative attachment in these sources, assuming steady state. And the values that were derived from the astronomical observations are shown here. So the last part of the talk, let me just briefly show you some fairly recent astronomical work in which we're now trying to understand more carefully the distribution of the negatively charged molecule with respect to its neutral counterpart in this source IRC plus into 16. Again, these are interferometric maps with the plateau de Beer, which is now being upgraded both in terms of the number of elements as well as the baseline. But this is a nice picture in the winter shown here. And there again, there are some molecules which are only formed in this central star or near the central star, while others are formed in this outer circumstellar shell. And again, this is time-dependent chemistry, whereby this is about equivalent in time to about 1,500 years. So our collaborators in France and Spain have looked carefully and developed various models to try to understand how these carbon chain anions, where they're abundance peaks, and using, in this case, a smoothly decreasing density distribution. But you see most of them are thought to peak at this typical kind of circumstellar distance, which I've already indicated here. C2H minus is only thought, if it's formed, to form in this very close to this central star because of the perhaps reactions with H minus. And this is a calculation for CN, where CN is peaking, and then where they thought, or we thought CN minus was going to be peak, and shown here is where we believe, based on the data, it actually is peaking. So it's peaking much closer into the central star than originally expected, and it's closer in than the radical. So this is yet another picture as well, simulation in the source IRC plus into 16, where in this case, just concentrate on the uppermost plot for the moment. You see the C6H radical is peaking at this characteristic distance, and the negative ion is slightly farther out, again, because of radiative attachment. So it should be formed slightly farther out compared to the radical, if this simulation and modeling is correct. And so what we've been able to do, the royal we in this case, is in fact now do a low-resolution interferometric map of specifically the anion. So keep in mind, negative ions not found in space until about 5 years ago, and now we're in fact to the point where we can do interferometric mapping, looking at the distribution in this source IRC plus into 16. So if you look here, it's not perhaps so convincing, but this is the distribution of the same transition of C6H radical and C6H minus. And you might argue, in fact, that C6H minus is perhaps slightly closer in than the radical, okay, which is not what you'd expect from this radiative attachment model. And what we've been able to do in fairly recently, in fact, is improve the resolution of these measurements. And in fact, that initial observation seems to have borne out. This, again, is the peak. This is the distribution, looking through a cut of this source IRC plus into 16. Again, this is where C6H radical peaks, and this is the same distribution of the anion. So the anion is peaking at a slightly smaller radial distance, which is an earlier time than the associated radical. This is, again, another slice through this source. And again, you've seen the same effect here, where we've overlaid the peak distribution for the negatively charged species as well. So this is not, perhaps given Eric's recent talk there, perhaps there's another formation route, but certainly doesn't not appear to be consistent with this strictly radiative attachment mechanism. This is now just another display of the spectrum in which we take the average intensity of concentric circles. So the HC5N is shown in red here, so that's these circles here, and its peak intensity is about here, about 15 arc seconds or so. The radical is also shown. It's a little bit hard to see in the spectrum, but it too peaks about 15 or 16 arc seconds. And C6H minus is shown in yellow, and that's peaking now about 12 or 13 arc seconds. So slightly earlier time. And we have different plots here. Again, C5N minus, we believe, is the carrier of these lines, though it hasn't been identified in laboratory. It has a very similar peak position as does C6H minus, about 12 or so arc seconds in. And again, this is another plot showing the same data here, where the peak intensity is shifted by a few arc seconds, so it's earlier time. So this is, I think, again, another illustration of where we can do astronomical spectroscopy, do time-dependent chemistry here, and more carefully look at this issue of the formation of these negatively charged molecules, and perhaps an indication now that what ultimately can be done on this and other systems. So in conclusion, at least from the maps, it appears that C6H minus and C5N minus are at smaller radii, which is earlier time than predicted. I didn't show because the data is not as good and less certain, but the opposite may be true for C4H minus. As I've already indicated, the abundances specifically of C4H minus and CN minus disagree with formation strictly by electron attachment, and the present work provides some constraints on the rate of electron attachment in these sources. So I think I'm almost out of time, but what I hope I've shown you is laboratory and arguably astronomical spectroscopy of negatively charged molecules is flourishing, right? Again, in only a matter of a few years, we have accurate rest frequencies for a number of these carbon chain anions. We see surprisingly high abundances, specifically of CH minus in the source IRC. The ratio is fairly constant in the sources where we have found in other sources. And we hope in laboratory and ultimately in space to extend the spectroscopy at high spectral resolution to a number of other small hydrocarbon systems and other species as well to, again, explore better the distribution of negatively charged molecules. There's a lot of work to be done ultimately to better understand the reaction rates, electron attachment processes, and other formation routes, as well as to properly account for these anions in chemical models. So I will then just acknowledge a number of people, my colleagues, Pat and Carl, and a number of other postdocs who were involved in the work, as well as a number of senior collaborators abroad who've been very helpful in terms of looking at these molecules in space. So I will end very much, and thank you very much for your attention.
Yes. Yeah, so both you and Eric mentioned grains, but mostly in terms of the source for electrons. I'm wondering if...
I don't know if I mentioned grains, but I did.
They were on it.
Oh, okay, maybe I did.
So I guess that's the question is, you know, can the grains be involved in the sequential reaction that builds up your C6H parent molecule?
Well, the formation of the radical itself or the anion? I mean, the normal routes for these hydrocarbons are gas phase reactions involving acetylene. So I don't think you build up from, you know, acetylene and then reactions of C2H very, very rapidly build up these longer carbon chains. So normally grains are not invoked for these hydrogen deficient molecules.
Yeah, so the neutrals, they're bent?
No, these are linear.
The neutrals are
Yeah,
linear.
so these are double sigma type states. So they're...
Why is there such a big dipole moment change? Now I realize you have to tell us the origin when you're given the dipole moments of the tribe species, but some of these are jumping 5 or 6 divide.
Well, in the case of C4H, there are two states, a double sigma and a double pi state. So one state, they differ by a fairly large factor in dipole moment. So it depends which one is ultimately the ground state. So when you go to longer chain lengths, you go from C2H to C4H, those are both double sigma ground states with small dipole moments. And then when you go to C6H, C8H, and longer chains, but this doublet pi state becomes lower in energy.
The pi should be bent. That should be a ring and pellet.
It is a linear, but there's a lot going on. And there's a very low-lying state, but we can fit them as a doublet pi linear system.
So in the larger ones, the dipole moments are large enough that these will have dipole bound anions. So you would think that at least in the larger ones, the low energy electron would be first dipole bound, and then there'd be this interconversion over into the valence state.
Mm. Yes. No. I don't. I mean.
Given the dipole moment of the C4, that's not big enough. So C6
Correct. Yeah.
is
exactly.
big enough.
Exactly. Yeah. You get the kind of typical 2 or so to buy.
Yeah, I think it's tens of MeV.
It's very low.
It's very low. But
Yes.
if this could rapidly then interconvert over to the valence state, and there's lots of evidence in the system, these can be doorways into the valence state.
Yeah, big literature.
Yeah. We had for a long time we had a problem looking at detecting C4H minus, and we thought it perhaps was this mechanism. And we still don't fully understand why, under some expansion conditions, we get actually very strong lines. In other conditions, we get very weak lines. And we thought for a while, in fact, the explanation was it was simply populating the double pi state, which has a large dipole moment. But anyhow, it's something we have thought a little bit about. But in terms of experimentally, we don't have much to say about that at this point.
C4H minus has just been detected in PNC1.
I did not know that. Who did that? Were we involved in that or someone else?
No, it was someone else.
Oh, okay, well. And I presume the ratio, it's, well, I don't know. And interesting. Interesting.
I think it's very close to what
I remember this paper actually from Petrie for the formation of Cl- that was suggesting like the dissociative electric attachment CN, magnesium CN. Is it this thing has been rolled out, or it's still?
For the carrier of
Yeah, it's like electric attachment of MgCN leads to like CN minus.
MgCN.
Yeah.
It's a carrier for the I'm confused. You're talking whether it's a carrier for B1377 or
I don't know. I just remember this paper from a paper.
there was a I remember that paper, and there was a possible detection of there's two series of lines in IRC plus 216. One is at 1377 and one is at 1395. And 1395 is a doublet state, which I think he may have suggested was this magnesium NC or CN, but which we have shown, in fact, is a low-line vibrationally excited state owing to things like Renner-Teller effect of C6H radical. So that turns out to be somewhat less interesting. I still think that's a good candidate, but it's not the carrier of the lines that we found.
Now, do you observe, so again, for something like your 6 carbons in a row, but with, say, 2 hydrogens, or 8 carbons in a row and a couple hydrogens?
Those must exist, but we can't observe them by rotational spectroscopy because they don't have a dipole moment.
What about the ion of that? You still couldn't see it?
No, it'd be nonpolar as well. But I mean, in terms of the carbon chain radicals, we can go up to C14H, for example. We've seen carbon chain radicals that long, and if we can somehow impart a dipole moment, then so there's no doubt that they exist and are produced in our discharge expansion, and perhaps as well as in space, but we can't see them.
What about if you have an anion? A bunch of carbons and have a nitrogen.
Yeah. So.
Bunch of carbons, nitrogen. Those are
Yes. So those are So there's the cyanopolyines, for example. In the laboratory, we did up to HC19N. So you can really run these carbon chains through quite long lengths. There's the radicals, which you can see. And then you can play other games. You can switch the CN group and make the ISO and all sorts of different things.
And what about molecular ions?
Well, we have CN minus and we have C3N minus.
I mean the plus.
Oh, yeah, we haven't found those yet. That's one thing we'd very much like to detect. For example, C3H plus was detected, or reported to be detected in space quite recently, and that has a closed shell sigma ground state. So that actually has many of the same properties in some sense as the anion in terms of the spectral light compression. C5H plus has the same, but we actually haven't looked for those recently. But it's a question of how to form the cations in that sense. We have no problems forming protonated species, but just to kind of rip an electron off a radical is proven more difficult than add electron to a radical.
You might mention, some of those you just mentioned react with high H2,
Well, yeah, but you don't necessarily in the laboratory have to make them with H2 or involving much hydrogen. I'm not bothered by that.
Well, the C3H plus does react slowly with hydrogen. Well, it's only seen in low density jet. Yeah. No, I'm just saying that it doesn't react fast with H2. C3H plus? Yeah. According to Gerlitz, that
So we should look for them.
All right, why don't we thank our speaker.